So I've been doing a lot more calculations concerning chronology, and I have to remind listeners that gyrochronology is something that the dogma has accepted to be true with reference to stars, and that the stars don't cool down and become planet-like. Unfortunately, we can go ahead and say that that's false. We have stars that cool and collapse and lose their angular momentum as they evolve. And we know this because their total angular momentum decreases as they age. And I put a little graph here. I'll link this to the bottom. This is on my Stellar Metamorphosis blog, not on a Vixra paper, but Venus, Mars, Earth, Uranus, Neptune, Saturn, Jupiter, Luyten star, Proxima Centauri is right there, TRAPPIST-1, T-Garden star, and the Sun. The line of best fit, I think, that's right here, which means the Sun is probably much closer to 100 million years old versus, the, what do I have that as? 10 to the 7. That would be 30 million, a little bit over 30 million, like 60 million. Probably more closer to 100 million years. I originally had another spot for the Sun to be like 3 million years. But I think it's more along those lines, between 60 and 100 million years old. As well, the total angular momentum is up here. So you have very low angular momentum, obviously not zero. There's 1 right there. But remember, this value is 1 times 10 to the 30. You have to add 1 times 10 to the 30 to each one of these values. And then it's in the standard measurements, which are kilograms per meter squared per second. And that S-1, that's per second, because that's what you're supposed to have on the denominator of the value. So basically what we have here is stars that have lots of angular momentum. They're huge. They spin with a whole hell of a lot of energy. And as they cool and collapse, that total axial angular momentum diminishes. And since this is my very first graph concerning angular momentum, it's only natural to look at this and think, well, clearly it continues up and up and up and up and up. And yes, that's exactly what I think happens. As you get to younger and younger stars, you have more and more angular momentum. Meaning if the star is dense, extremely dense, and spinning really, really fast, it's going to have more angular momentum than even the Sun, which is really, really large, but spins pretty slowly. It does 1 rotation. Of course, there's differential rotation. I think the equator is, 38 days that it rotates. It takes 38 days to make 1 rotation. And I think at the poles it's like 25 or 26, I can't remember. But, about a month for the whole thing to spin around once. And that's really, really slow. But it has a lot of mass, so you have to take that into account. And it has a long, it has a long radius, so it's very wide diameter. It's really, really big. So even if it doesn't even need to spin all that fast, because it's just so huge that it carries all the angular momentum with it. Think of like a fast spinning Lego wheel versus a truck tire. A truck tire would spin a lot less than a really fast spinning Lego wheel. But I guarantee the truck tire will have a lot more angular momentum on the axle than a little Lego wheel would. As well, I wanted to make this specific line of fit here because, as you see, Jupiter and Saturn are over here, and Luyten star and Proxima Centauri are over here. these things are spinning really, really slowly. They only have a little bit more angular momentum than Jupiter. Actually, okay, Jupiter, let's put the values right here. Jupiter's angular momentum is about 4.49 times 10 to the 38 kilograms meters squared per second. And I took the dimensions away so people can, if they're not good at exponents, they can imagine what that is. That's 4.5. And then Proxima Centauri, it spins at around once about 82, 83 days. But it's really massive. It's like 0.12 the mass of the sun. So even though it spins slow, not every 10 hours like Jupiter does, it has a lot of mass. So it still has a value, dimensionless, of almost more than double Jupiter. And then you have Lewin star, which is another red dwarf. It has a bit more, spinning a little bit faster. And you have, let's see, TRAPPIST-1, that's spinning a lot faster. And then you have Teegarden star, that's spinning even faster than those, even though all these red dwarfs are about the same mass. Vary a little bit, like 0.08 sun masses to 0.12 or 0.15 sun masses. And then you have the sun. Of course, I made the sun's value dimensions list as well, but it's the dimensions over here, right here. So 9,032.7, which is clearly a lot more. And then you have this is the angular. This is the tangential velocity. This is how fast on the surface is spinning. So 10 plus or minus 4 kilometers a second, which works out to 561. That's the dimensionless limit on here. But then I put plus 224.4 plus or minus that. So it might be a bit lower. It might be around 300, and it might be around 700. Of course, I'm also taking these values and I'm hoping that they're correct, because I'm making ideas revolve around these values. If the values turned out to be wrong or a measurement error or something, then the work I'm doing is going to be wrong too. So I have faith in these people that they know how to measure how fast the star is spinning. Again, this is important because the amount of mass and how fast it spins can be used to determine its total angular momentum. And the important part here, and this is where astronomers completely drop the ball, is that stars like red dwarfs like Teegarden star and TRAPPIST-1, Proxima Centauri and Lewin star, those cool and collapse and lose their angular momentum as they lose their mass, and they become gas giants, similar to Jupiter, Saturn, Neptune, and Uranus, and it continues. And this is basically another type of WT diagram, if you will, but this is axial angular momentum. Let's see, some other ideas here. What else do I have? Okay, and two important ideas before I close out this talk. I want people to understand that there are two main principles of conservation regarding star evolution. There's mass conservation, the conservation of mass, and there's a conservation of angular momentum. Meaning, for a closed system, a closed system meaning there's no net transfer of mass, the mass is going to be conserved. Clearly, that's common sense. If there's no mass entering or exiting the system, the mass is going to remain the same. The same thing with angular momentum. If there's no net transfer of mass into or out of a spinning body, then the angular momentum is going to remain conserved. As well, you have to factor in, things like friction or tidal forces, and it gets really complex really fast with what I'm working on right now. And I'm just trying to get the basics down. And the basics are, you have, this is the This is the angular momentum equation. You have total angular momentum, and then you have your I, which is your moment of inertia, and then you have your angular velocity, which is the omega. And you just take, it's pretty simple stuff. You just take the omega and the I, and you multiply them together, and you get the angular momentum. And the reason why I'm saying this can get really complex really quickly is if you, this is gonna be kind of stupid, but I'll write it down for you guys. All right, hopefully this makes sense. Here's the normal equation. Now, if you increase the moment of inertia, you decrease the angular velocity. So those two have to equal out. If these two L's are equal, then this, and this is a lot more, then this is going to shrink. Also the reverse. If you have the moment of inertia decrease, then the angular velocity will increase. Now what this is a figure skater pulling her arms in, and this is a figure skater throwing her arms out. So when the figure skater throws her arms out, she increases the moment of inertia and decreases the angular velocity, so she spins slower. And this is when she brings her arms in. She decreases the moment of inertia and she increases the angular velocity. This is why when you see in the Olympics, when they pull their arms in, they spin faster. All right, guys, later.